Boundary effects, reflection and transmission. In this session, we will explore how waves behave when they encounter the limits of their environment. We will start by examining reflection from fixed and free boundaries to understand how the end of a medium affects a pulse. Then, we will look at what happens at junctions where two different media meet, leading to both transmission and reflection. Finally, we will establish general rules for when a wave undergoes inversion based on the properties of the materials involved. Previously, we often modeled waves as traveling through an infinite medium without any interruptions. However, in the real world, waves eventually hit a boundary where the medium ends or its properties change. Think of an echo bouncing off a distant cliff, or a pulse reaching the end of a telephone cord. When a wave pulse reaches such a boundary and moves back along the medium in the opposite direction, we call this process reflection. Understanding these interactions is essential for describing how energy moves through finite systems. Let us first consider reflection at a fixed end, such as a string tied tightly to a heavy, unmoving support. When an incident pulse reaches this rigid boundary, it exerts an upward force on the support. According to Newton's third law, the support exerts an equal and opposite downward force on the string. This reaction force creates a reflected pulse that is inverted, meaning it is upside down compared to the original. If the incident pulse was a crest, the reflected pulse returns as a trough, representing a 180-degree phase change. Now imagine the end of the string is tied to a light ring that can slide freely up and down a frictionless post. This is known as a free boundary. As the incident pulse reaches the end, the ring is free to move and accelerates upward to the height of the pulse. Because the end can move, there is no downward reaction force from a support. Instead, the tension eventually pulls the ring back down, creating a reflected pulse that is not inverted. In this case, an incident crest returns as a crest, maintaining its original orientation. When a medium does not end but instead changes into a different material, we encounter transmission. At such a boundary, the energy of the incident pulse is split. Part of it is reflected back into the first medium, and part is transmitted into the second. Because of the law of conservation of energy, the sum of the energies of the reflected and transmitted pulses must equal the energy of the original incident pulse. This means the reflected pulse will always have a smaller amplitude than the pulse that started the process. Consider a pulse moving from a light string to a heavier, denser string. The junction acts somewhat like a rigid support because the heavier string is more difficult to move. As a result, part of the pulse is reflected and inverted, just like at a fixed end. The remaining energy is transmitted into the heavier string. This transmitted pulse is never inverted. It moves forward with the same orientation as the incident pulse. In the diagram, you can see the reflected pulse returning as a trough, while the transmitted pulse continues as a crest. If we reverse the situation, so a pulse travels from a heavy string to a lighter one, the behavior changes. Here, the lighter string acts more like a free end. When the pulse hits the junction, the reflected portion is not inverted and returns with its original orientation. We can also look at the wave speed, which is equal to the square root of the tension divided by the mass per unit length. As the pulse moves into the lighter medium, where the mass per unit length is lower, the wave speed increases. Again, the transmitted pulse remains non-inverted. We can summarize these behaviors into two general rules for reflection. Rule 1 states that when a wave travels from medium A to medium B, and the speed in A is greater than the speed in B, meaning the second medium is denser, the reflected pulse is inverted. Rule 2 states that when the speed in A is less than the speed in B, meaning the first medium is denser, the reflected pulse is not inverted. A vital point to remember for both cases is that transmitted pulses are never inverted. They always keep the same orientation. To wrap up, remember that reflection at a fixed boundary results in inversion because of the reaction force described by Newton's third law. In contrast, reflection at a free boundary does not cause inversion. When waves encounter a junction between two media, the energy is shared between reflection and transmission. Whether the reflected wave flips depends entirely on the relative wave speeds and densities of the two materials. These principles allow us to predict how waves will behave in complex, multi-layered environments. To check your understanding, consider why a pulse at a fixed end undergoes a phase change while a pulse at a free end does not. Think about the forces involved at the boundary. Also, if a wave moves from a medium with high wave speed to one with lower wave speed, will the reflected component be inverted? Use the general rules we discussed to explain your answer. These concepts of inversion and energy splitting are fundamental to understanding more advanced topics like standing waves and interference.